All right, we're back. Now we're shifting to information about the discrete time Fourier series. We've been talking about continuous time, but the main focus of this semester is on discrete time. And so I say this is big. So this is big time important. We're going to spend the bulk of the semester on looking at discrete time signals. Here's the deal. Periodic signals have Fourier series. Discrete time periodic signals have a discrete time Fourier series. That sounds simple enough, doesn't it? Oh, by the way, I want to mention these notes are available for download in the lecture 18 PDF file, which is on the website. So if you want to follow along, that's the best way to do it. Just download and print those out. All right, back to the lecture. Remember that we're talking periodic, so the definition of periodic is a signal is periodic if for any value n, little n is the time variable, we can find some non-zero big N that makes this true. So if we do a time shift of big N times big N samples, we get the same thing as we got before we time shifted. So this has to be true for all n, and then it's a periodic signal. Well, here's the discrete time Fourier series. It's for a periodic signal. If that's true, we say that x of n can be written as an infinite sum of weighted complex exponentials. Very, very similar to the continuous time Fourier series. Okay, but in continuous time, we had a t variable, continuous time t up here in the exponent. Okay, so that's the synthesis equation, the inverse transform. The analysis equation, where we come up with the CKs, is a little different because before, when we had x of t, this was an integral, right? But now x is discrete, so an integral doesn't work. We use a sum. So it's very, very similar. We had 1 over t here previously for the continuous time case. Now we've got 1 over n, where n is the period. Okay, so it looks very similar, except now n is the time variable. All right, so we won't go about trying to derive that. You can look in the book. They've got a nice discussion. I want to point out that these limits, n equals 0 to n minus 1, you sum over any full period of the waveform. And here you sum over any full period of the spectrum. Okay, the sum here looks like it's fixed, 0 to n minus 1. That's not necessarily what you have to do. You can pick any convenient full period and form that sum, and it works just fine. This is usually the way it's written down because usually this is implemented on a computer, and computers don't care how hard they work. But if we're doing it by hand, sometimes we can find a set of limits that makes it easier. All right, so we can sum over any full period. Well, all right, we know x is periodic. What do I mean by a full period of c? Well, we've discussed that earlier, and I'll discuss it a little bit more in a minute, but discrete time signals have periodic spectra. In other words, the CKs are periodic. So we'll talk more about that in a minute. Well, just as with the continuous time Fourier transform and Fourier series, there's a Parseval's relation that tells us how to interpret the Fourier coefficients. And for discrete time, it looks like this. The average power, now this is the time average. Remember, we had a time average of power for continuous time, but this is the time average. 1 over n times the sum is the time average. So this is the time average of the signal power. So that's the total average power in x. X squared is power. And you sum it up, you get energy. Divide by n, you get power. Well, this thing on the left side is what Parseval came up with. He says, well, we got to have the total power has to be the same in the frequency domain, right? So we sum up all the Fourier coefficients, magnitude squared. Well, with a little bit of interpretation, the left side has units of watts, its average power. So think about it in terms of watts. although we have to be careful how we interpret that. We'll talk more about that later. The right side also has units of watts. Okay, so these magnitude squared Fourier coefficients are the average power in the kth harmonic. Let me underline that so you understand what that means. It's the average power in the kth harmonic. Okay, since we're doing a Fourier series, there are harmonics. Okay, if we plot the magnitude squared of the Fourier coefficient as a function of frequency, which could be little f or little omega, remember those are normalized, or big F or big omega, those are in regular units of hertz and radians per second. Or sometimes we plot versus k. K is just the frequency index. All of those are called the power spectrum of the signal, because the ck squareds are power values. All right, I said that the spectrum of discrete time signals is periodic. And we can say that, and I'm going to prove that right now, just so you get an idea where that comes from. Again, so here's the bottom line. The spectra of all discrete time signals is periodic. All right, we showed in class that it works for a sinusoid. For a sinusoid, if we take f and we replace it with f plus n, we get the same result. So clearly, for a sinusoid, it's periodic. Right, and we can also say that if we replace omega with omega plus 2 pi, that's the same equivalent statement. All right, so we showed that. But let's extend it to all discrete time signals. What I want to show is that the Fourier coefficients, which are a function of k, the frequency index, are periodic. So you can take any k. If you find the period n actually is the period, right? It's a number of samples in a period. Which we've actually spent a lot of time on. So the spectrum itself is periodic. All right, and let's just prove it. Here's the Fourier coefficients. If I take k and replace it with k plus n, okay, it now becomes k plus n. Let's see what we get. Well, I can factor out that k plus n into one term that's got k, and then I've got the term with big N is e to the minus j 2 pi big N over big N. Okay, the big N's cancel, and I just get e to the minus j 2 pi times 1, right? So I'm factoring that exponentials are so nice to work with. We can just, if they're additive terms in the exponent, then we can factor them into two multiplicative terms. And this, I hope everybody knows by now, is just 1, okay? We've got a multiple of j2 pi in the numerator, either plus or minus j2 pi, k is an integer, so that's just 1. All right, now, since that is the same as ck, so those are the same, it's periodic. All right, well, let's work out a couple of simple examples. Find and plot the magnitude and phase spectrum for this signal. All right, so we're just going to plug this signal into the discrete time Fourier transform. Well, if ever you see a signal that looks like that, that's made out of sines and cosines, your first thought should be to see if it directly maps into the Fourier series itself. All right, and one way to do that with sines and cosines is to replace it with the Euler identity. Remember that a sine x is 1 over 2j e to the jx minus e to the minus jx. All right, so if I break up this sine wave, it becomes 1 over 2j e to the j 2 pi 3 n over 10 minus 1 over 2j e to the minus j 2 pi 3 n over 10. Okay, now compare that to the discrete time Fourier series. shown here. It should be very clear that these are the same sort of, this is the same form where we have a constant times a complex exponent. And we've got several of them, in this case 2 of them. By inspection, if you look at this, it's clear that the period of this signal is 10. We did a whole bunch of homework problems. The period of this is 10. So that's by inspection. And furthermore, if you look at the 3 and compare it to the k, you see that k is equal to 3 there, and k is equal to minus 3 for this term. So ck is just a constant multiplier, which is 1 over 2j, and if you take j to the upstairs, you get a minus j on the numerator over 2, and we can write that as e to the minus j pi over 2. Okay, that's sometimes very nice to do. The c minus 3, that's this coefficient, is minus 1 over 2j. But, you know, sometimes we want to get it into values of k that go from 0 to k to n minus 1. And we notice that minus 3 is not in that range. However, we know the ck's are periodic. So we can take any c3 and add n to it. So c minus 3 should be exactly the same as c minus 3 plus 10. You got that? So I have a minus 3, but I want to figure out where that is. Since it's periodic, there's got to be an instance of it in this range. So we go ahead and add n equals 10 to this, to k, and we get the idea that c minus 3 is the same as c7. Okay, so c7 turns out to be j over 2, which is 1/2 e to the j pi over 2. Oops. So now we're in a position to sketch out the magnitude spectrum. Magnitude of ck. Both of those coefficients have 1/2 as the magnitude. So there's the c3 and this c7. They both have a magnitude of 1/2. And since we put this in polar coordinates, it's clear that the phase of c3 is minus pi over 2, and the phase of c7 is plus pi over 2. So that's where we get this. This pi over 2 comes down to there, and this minus pi over 2 without the j is this guy. Okay, so there's the magnitude and the phase spectrum.